So, okay, yeah, what that's looking for is, and this is actually a great time to talk about this, is the Proctorio app is designed to look for cheating behaviors, okay? And so basically what I want you to do is I want to see what you've, gotten into your head. I want to see no books, no notes. Can you answer the questions, And so it's basically looking at how long does it take you to answer the question? Are you answering the question and thinking about it, or are you like going over here and looking at like, oh, my notes and stuff like that? So what it's looking for is what it considers suspicious behavior. Just pondering off to the side is not a problem, or looking down and writing like that is not a problem. But if you are flipping pages or, trying to take pictures of it and put it on CHEM, it'll flag you right away for those things. Okay.
Okay. I was like, I got 3 kids and they're constantly like, I want something to eat. I'm like, okay.
Yeah, no, and those kind of things, what it'll do is it'll flag every once in a while. If you do a lot of it, it'll lock you out. But that's why I live monitor. And so that I can have a Zoom, I'm gonna have a Zoom window open during the exam. And so you can come in and say, hey, it locked me out, and I can look and see what the behavior was. And then we can go ahead and unlock you and do that. The key here is that, if you as the student, not you personally, but you as a student, consistently are doing a behavior that is what they consider unethical. And for example, you're making all, a certain score, and then all of a sudden on the final you're making 100 and you were looking way a lot. That's suspicious. If you have a personal, I move a lot, so it kind of flags that. Well, I would recognize that, and my students say, oh, well, that's something they normally do, so that's not a problem. What it is it's bringing up, suspicious behavior or changes in behavior that weren't previously seen. Okay. So that's what we're really looking for in the Proctorio side. And I actually reviewed the Proctorio stuff with Top Hat today, and I can change levels of sensitivity for different students and stuff like that. What I'm hoping for is that, we're a nice small group. We're all going to be ethical and try to not cheat, do our best, making an honest C is better than making a cheated B. And that with the Proctorio, I would have evidence to take to an ethics council if I had questions. So that's the whole point of it is, that's the whole point, is that in this environment where I cannot monitor personally, this is a good opportunity for it to be monitored and you still to have a reasonable, non-threatening, testing environment. Okay.
Sounds good.
Any other questions on that while we're here? Because that's a great question. So what I will be doing is tomorrow, I will be emailing out a Zoom meeting that's just for our exam time, okay? And so I will be live monitoring Proctorio, and what it's gonna do is it's gonna say whether you're writing or whether you've submitted or whether you got locked out, okay? If you get locked out for a behavior, go ahead and go into the Zoom meeting. We'll talk about it. I'll reopen it, and then we'll try to figure out, why it kicked you out and make sure that you're, getting the best opportunity to make a good grade. Well,
so is it gonna flag us for and kick us out for? Cause so I'm a person, I talk out loud a lot to myself when I'm thinking, and I saw that it tracks mouth movements and stuff too. Is that something that it's gonna maybe flag me for? Cause I live alone, so I won't be talking to another person besides.
That's not that'll be flagged as look at this behavior, and then I can look at it and say, oh no, that's just talking to yourself. A lot of things it'll do is when a second person comes on, or if you are constantly looking over to the person on the other side of the camera who's viciously typing away on Google trying to get answers, and then hearing them speak, or you're doing this, it'll start to see those behaviors as being suspicious.
Okay.
So your individual idiosyncrasies are not going to be a determining factor, but you know, it might flag you the first couple times, but then it'll get used to what you're doing.
Gotcha. Okay, cool.
Okay. So it's all about, I really want you to take the exam, close note, close book, just as if you would take any other exam. You can have some spare paper, draw some stuff out, think about things, and give us, you know, give me the best answer you can formulate at the time. But, you know, avoid cheating, avoid, you know, things that you would not be able to get away with in the regular class. Okay. So look at it that way. I'm trying to give you an opportunity to, you know, tell me what you learned in an honest fashion. And, you know, the fact that you're being recorded is hopefully going to keep everybody honest and keep everybody, you know, trying to get the best grade they can get with the opportunity we're creating here. Okay.
So just one last question to be clear. So no notes, no book, no phone, nothing. However, you mentioned maybe some scratch paper. What?
Yes.
I mean, how would Proctorio?
So when you're looking at scratch paper, it's going to be like something in front of you that you're doing this. It actually listens for flipping of pages and having a second computer. If you're constantly looking over here and doing this, then it's going to say, hey, they have another computer they're trying to do something on. So just looking down and thinking about it, looking at the question and, you know, drawing it out and saying, oh, okay, that's what it is, and click. Those are normal behaviors. That's what I would expect to see during giving a test in class. And so that's a normal behavior. It's when you start doing flip, 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 and, or, you know, to somebody off camera, that's when, or somebody else gets on camera and says, oh, it's error. That's all things that are, number one, things we wouldn't have in a regular class. Number two, things Proctorio looks for.
Okay.
Okay. So, I mean, it's just trying to keep us, you know, being the same kind of procedure we would have in a regular class, except we get to do it in the comfort of our own home.
Okay,
I apologize. I have one question regarding the materials that we can use. So for the periodic table,
Yes.
I have like a small amount of notes on there just so that I can remember a few things. Like I have like the S, the D, and the P orbital portions noted and things like that, but no like actual like handwritten like paragraphs. Am I allowed to have that, or do I need to use like a completely blank one?
What I would like to do is tonight I'm going to email you out what I want you to use. Okay, it's the one that the ACS allows us to use, and so that's the one I would like you to use. And it's basically the blank sheet of paper with just the table that I had that I showed you before. I'm actually trying to figure out how you can use that as a reference during quizzes. I haven't quite figured that out yet, and I will email you a PDF of that one. And so it has all the numbers and everything in the groups, right? But it doesn't have P, S, and F and all those. But I will be emailing that out today, the one I prefer you to use.
Will there be a way, like I don't have access to a printer right now, and I know you said you're trying to get a way we can use it during quizzes, and I guess by that you're meaning to use it on top at like while we're taking an exam. Will that be possibly available by tomorrow for the exam, or is there another way that I can have that up in like a separate window or something?
Cannot have it on your computer because the Proctorio will block it out. But if
Okay.
you have a piece of spare paper and you just hold up a table of contents and your blank paper and put it in front of you, that satisfies me for you know, showing me what's in front of you.
Gotcha. Okay.
Okay.
Thank you.
So, you know, if it's only like an S and a P here and there, that's probably acceptable. But you know, you want to basically just a blank table of contents and a couple places of blank paper.
Okay, cool.
And I think that's appropriate. Okay. Okay, great conversation, by the way. Thank you. I'm glad that led into that. Okay, so what we're going to do is we're going to go ahead and see if I can get my computer to share again. My iPad has decided to look on a different, Wi-Fi connection. Come on. I talked too long. Okay, stop sharing. Let's try to reshare. There it is. Okay, so that's got us to resharing again. Okay, so what I'm hoping to do is get through chapter 4, goals 1, 2, and 3, and then with the remaining time, we'll do an exercise with cyclohexanes. And it'll be something that, you know, we're going to draw, you know, you can have paper and we can draw, just kind of showing you the idea of how things flip back and forth a little bit with the cyclohexanes. If we don't get it to today, that's fine. I think we spend our time, you know, talking maybe additional questions. If you have questions about the exam, let's go ahead and get like any, you know, fears or questions about that out of the way. I think that's more important. We can always catch up on that exercise later. Okay. So again, I have the chat open here. We have a small enough group. If you have a complex question, go ahead and unmute and ask it, and we will continue. Okay, so alkanes, not many reactions that we have there, and it was all about the, you know, sp3 hybridized bonds. Well, once we go to the alkenes and alkynes, we have the idea that we have sigma and pi bonds, and we have a slightly different hybridization. After we understand that and the hybridization and the shape there, we're going to go on to nomenclature and then show again physical properties and the types of bonding they do. Okay, so our goal 1 is the idea of sigma and pi bonds. Okay, so when we first, in our first chapter, we talked about the different energy levels, and our principal energy level is starts out at 1, and there's only 2 electrons available to us, and things like hydrogen and helium are there. Once we get to the principal energy level 2, that's where we have carbon, nitrogen, oxygen, and fluorine, and that's where we can get to those additional bonds, the S spherical bonds and the P dumb shell bonds. Okay, and so as we fill the electrons up, we have an opportunity to start blending energy orbitals in the same energy level. Notice they're all in the same energy level. We're not blending across energy levels, okay? When we blend those into it, hybridized orbitals will always form sigma bonds. Unhybridized p orbitals will form our pi bonds. I think that is a very significant thing that if you keep track in your mind, you'll say, oh, if I have an sp3 hybridized carbon, I have no pi bonds, I have no p orbitals, I cannot have any pi bonds. If I have an sp2 hybridized, I have 3 equivalent orbitals, meaning I have to bond that p to something else. And where should it be? And if I only have an sp, that means I have 2 p orbitals I have to play with. That means I have to have 2 bonds somewhere. Okay, so that's the key we have to think about when we think about hybridization and where the different bonds come from. Okay, so with the sp3, they're all equal. So we have 4 equal bonds. They're all of equal energy. They're all of equal shape. Okay, with the sp2, we have now 3 equivalent orbitals plus that 1p. That changed our shape. Okay, only the hybridized orbitals can form direct bonds or sigma bonds. Okay, the unhybridized p can make parallel bonds or pi bonds. Okay, and as we move to the sp, we can now bond 2 times to sigma bonds because we have 2 equivalent orbitals and those 2 p orbitals there. This is, you know, if you can visualize this, this is going to make all of our other functional groups very easy to understand. Okay, so sigma bonds are the direct hybridized orbitals, pi bonds are the parallel p overlapping orbitals. Okay, so when we get to the point where we don't have an sp3 hybridized carbon, that's where we get to unsaturated hydrocarbons. Okay, and if we have 1 double bond, it's an alkene. We have 2 double bonds on between 2 carbons, it's an alkyne. Okay, and that's where the reactions happen. Again, alkanes have very few reactions. the electrons on the outer side, the electrons in those p orbitals are outside the mass of the two atoms, right? They're sticking above and below. That's where reactions are going to happen. So when we start thinking about alkenes and alkynes, think, oh, they're going to react with those p's. That's where a lot of the chemistry is going to happen, okay? It's still a nonpolar bond, but the electrons are outside the mass of the two atoms, okay? That being said, because the pi's are above and below that plane, we no longer have free rotation, okay? And without that free rotation, we now have a fixed geometry, which means we can have isomers, cis and trans isomers. Okay, so we can say cis and trans isomers if and only if we have one substituent on each of the carbons, or two substituents on the alkene total, okay? So if you have one carbon on one half of the alkene and one carbon on the other half of the alkene, you can have that cis-trans isomerization. If you have more than two things bonded to your alkene, you must use E and Z isomers, okay? But with simple things with just one attachment on each side, cis and trans works fine, okay? If you have an alkene at the end of a chain, you now have two equivalent hydrogens, you do not have any isomerization. So at the end of a chain, you don't have isomerization. In the middle of a chain, if it's a straight chain, you can have cis-trans isomerization. In the middle of a chain with a branch point, you can have E and Z isomerization. Okay, so the alkyne, being that it's that linear thing and has two overlapping pi orbitals, makes it very, number one, noticeable. Number two, it is linear, and you have an opportunity to react each of the pi bonds separately, okay? So you can react just one pi bond, or you can end up reacting both pi bonds. And we'll see that when we look at the reactions in chapter 5. Okay. Now, because the alkyne has sp hybridized carbon, that changes the acidity of the hydrogen, okay? The alkane has sp3 hybridization, and because it's sp3, the pKa of that hydrogen is 51. That's not very acidic. It's the weakest acid we have, okay? Because of the alkene has sp2 hybridization, and so that's 3 equal bonds, its acidity increases to approximately a pKa of 44, but having it been down such that there's so much more S character, so much more spherical character in that sp hybridized alkyne, that sp hybridized alkyne is the most acidic of our hydrocarbons at 25, okay? And it has everything to do with the hybridization, okay? It's not because it's sticking out there in space, it's because it's the hybridization. And the fact that spheres can balance charge better than the dumbbells because it's more surface area. So you can think about that. The alkyne has sp, which is half round, half dumbbell. It has more space to spread out the charge, therefore it is more acidic. Okay. It's kind of a visualization on how it works, but I think it works really well. Okay. Questions about those things, okay? So the hybridization tells us that we can have a double bond. The hybridization also gives us an idea about acidity of those compounds. All right, I'm gonna stop sharing. Go ahead and tap any questions you have in, and I will move to this next one. And goal 2. Go ahead and share. There we go. Okay, so the nomenclature of the alkenes is a little bit different than the alkanes. Number one, the infix, the En, tells us we have a double bond. The In, the Yn tells us we have a triple bond. But then we have isomers available to us that we didn't have in the alkanes, okay? So again, the prefix En is a double bond, Yn is a triple bond between two carbons, okay? Now, you might accidentally think, oh, there's a double bond here and a double bond here, that makes a triple bond. No, there's a total of that many p orbitals making double bonds, but it has to be a triple bond between two carbons to make it alkyne. Otherwise, it's a diene. So don't get those confused. They're not the same thing, but every once in a while, somebody confuses them, okay? So again, the infix, which is just the En, Yn, or An, tells us about whether or not there's a single bond, a double bond, or triple bond. The last letter, and in this case with the hydrocarbons, it's usually an E, has everything there's no other functional group. That's all it means, okay? So when we look at our nomenclature, it's important that our alkene be in the parent, okay? Both carbons of the alkene and both carbons of the alkyne have to be in the parent chain, okay? Even if you can make a longer chain, that doesn't matter. Like in the case of here, we'd actually have one carbon longer in this chain if we did not have both of those carbons, but because we're naming it for the alkene with the En, we must include it, okay? So it becomes the parent, and the extra part of the chain here is now a substituent, okay? Also, when naming alkenes, you need the first carbon of the double bond and the second carbon to be the two lowest numbers possible. Doesn't mean it has to be 1, because if we extended this chain out here, that would no longer be in the 1 position. It just means it has to be in the lowest position. And we had a couple of those we did in the video, but that's a subtlety that I think we should make sure that we keep in mind in our nomenclature rules. Excuse me. So, and the alkyne follows the same rule in the fact that the alkyne must be in the parent chain, and it must have the two carbons in the alkyne have the two lowest numbers possible. Okay. So, and then there are several of these that are used industrially, and therefore they have common names. So you might hear of things like, even though the IUPAC name is ethene for having a double bond with two carbons, so the Eth is two carbons, the En is a double bond, and the E at the end is no other functional group. The common name is the ethylene. And so it's like it's the substituent plus the functional group. So ethyl, would be a substituent. En is the functional group. And so when we talk of the common name or engineering name, it would tend to follow those rules. So if you have propylene, which was 3 carbons, that would be the common name. However, the IUPAC name would be prop for 3, En for double bond, and E for no other functional group. Okay, so that's the subtle difference between the common name and the IUPAC name. In most industrial type of applications, they will try to use the common name. Luckily, we'll be using as many of the IUPAC names as possible. Okay, so in naming alkynes, we follow the same rule, except for the Yn. Has to be in the parent chain, lowest numbers possible. And again, the E at the end has everything to do with the fact that there's no other functional group. There are things called ine-alls or ene-alls. We'll get to those later. But it's showing you that now, because that E has been removed and there's that other suffix there, we have another functional group. We have both functional groups. We have an alkene and an alcohol available to us. That's why we need to keep track of that last thing. Okay, so if, come on, nope. It's not, there we, okay, it did. Okay, it came back, yay, all right. So if we have the double bond inside a chain, and so it only has one carbon bonded to each side, we have cis-trans isomerization, okay? Now, when we do the EZ, we have two different axes to play with. When we do cis-trans, all we care about is the first axis. So in cis-trans, we have the first axis, which is the axis created by going through both carbons of the double bond. And if they're on the same side, then they're cis. If they're on opposite sides, like this one here, they're trans, okay? That's the first axis. And when we only have two substituents, we only care about that first axis, the one that contains both of the carbons in the double bond, okay? However, if we have more than those two substituents, we have to go to the EZ configuration. And in the EZ configuration, we have to consider two axes. The first axis is the axis that we are talking about, which is the same axis as in the cis-trans. So we're looking at whether they're on the same side of that axis or the opposite side of this axis. However, when we assign priority, we only assign priority to one side of the molecule or the other side of the molecule. So we split the double bond in the opposite axis, saying that, okay, we compared this side to this side. You do not compare this to this because they're on the same side of the alkene. We only compare cutting the double bond, one side of the double bond, cutting the double bond, the other side. That's the difference in the EZ versus cis-trans. You start with the same axis, and in the EZ, you add that second axis, okay? So if they're on the same, let's say primary axis or number one axis there, right here, they're both on the same, the two highest priorities on that same side, they are zusammen or Z, same side, okay? If they are on opposite sides of that axis, one's up and one's down, then they are hingegen, okay? So that's the big subtlety between cis and trans and E and Z. And then, excuse me, wow. But now we have to figure out what it means by higher priority. And it's as simple as the atomic number. Molecular weight usually works, but atomic number is the true name here. So hydrogen's always the lowest because it has the atomic number of 1. Carbon is the typical one we start looking at because it's usually the most common thing attached, and it has the atomic number 6. And then as we add other functional groups, they go up from there. So nitrogen, oxygen, sulfur, etc. Okay. So if there's only that one thing and we can differentiate there, we're done. But a lot of times we have like, okay, it's a methyl group or an ethyl group. Those are different, and therefore we have to go to the second rule. The second rule is if we can't identify it by the thing directly bonded to it, we have to look at the one bond over from that. Okay. So if all of these have the same bond directly to our double bond, we have to look at the next atom over, okay? So if all of it's all hydrogens, they're all the same, so they're all low priority. These hydrogens typically don't count. We look at the next priority number right up here. And most compounds will end up identifying priority just by looking at that next atom over. Okay. On rare occasions, we have to apply rule number 3. Rule number 3 is if you have a double bond, you have to think of it as, okay, one of the double bonds is to one of those atoms, and the other double bond is to another one of those same atoms. So in the case of ethylene, this carbon is bonded to a carbon and then bonded to a carbon. So that's what counts as it being bonded to 2 carbons. Where on the case of here, we would have this bonded to 1 oxygen for the first bond and another oxygen for the second bond. Okay. So that being said, the one with 2 carbons on it has a lower priority than the one with 2 oxygens on it. So on occasion, we have to use that double or triple bond rule, but most of the time, those first 2 rules will identify priority. Okay. The last thing is the idea that we can have cis-trans isomerization in cyclocompounds. However, that only starts at octene, okay? There is not enough way to twist the material around to get a double bond inside a cis-trans isomerization in a ring that is smaller than octene. So we typically don't have to worry about it, but it's a subtlety that I think we should pay attention to, because cyclohexene and cyclopentene only have one isomer possible. The bonds are not long enough to be able to do that cis-trans. Okay, and then the last thing is if you have more than one diene, you're going to follow pretty much the same rules, except of course you're going to try to get the first double bond to be at the lowest number, and all subsequent double bonds need to be labeled by which carbon they start on. Okay, so on this right here, we only have 7 carbons, so it's heptene. Okay, but we have 2 double bonds. So we're going to stick that idea that we have that second double bond in between the hept and the ene. So it's heptadiene, because we have 2. If we have 3 of them in there, it'd be heptatriene. Okay, but we still have to identify where those double bonds start. So we have these numbers here are all about the idea that, okay, if this is our first carbon, our first double bond has to start at our 2 carbon. That means our second double bond can't start at 3 because it's already taken up by the other one. So it must start at the 4. That's what these 2 numbers mean. You number the first carbon of the double bond to show you where it is. And then of course we can add the cis and trans isomerization based on the fact that it only has 2 substituents on each of those double bonds. All right, questions on chapter 4, goal 2. Okay, we're only adding to those previous rules. We're not taking away from the previous rules. We start with our parent chain, we do everything, we add our alkene, and then we look at whether or not we have an isomerization issue. Okay, if anybody has any questions, go ahead and chime in or put it in the chat, and I'm going to pull up goal number 3 right here. Yay, it stayed with me. Okay, so the last thing I want to talk about is physical properties. And just like with the hydrocarbons, we only have that dispersion forces with us as far as the types of intermolecular bonding we have. I think my coffee's making me cough. Okay, so the geometry of these materials have changed because it's trigonal planar because of the hybridization right here. But we've added no new polarizing groups. We've added no new polarizing bonds. So the primary forces we have here are the van der Waals forces, okay? But one of the key things these do have is that even though we're trigonal planar, we're trying to be that flat thing. The bigger the groups get, the more it spreads out. There's a little bit of bending of these bonds. Again, we're targeting 120, but the size of the group, the fact that the carbon here is larger than this hydrogen here, is going to spread that out a little bit. And in the presence of a carbon up against a carbon, this carbon's bigger than a hydrogen, and it spreads it out even more. Okay, still sp2 hybridized, still trigonal planar. It's just the size of those 2 atoms spreads it out just a little bit and changes its configuration ever so slightly. Okay. Of course, when we go to the alkyne, we don't have that kind of tension, that torsional force here, because it's already 180 degrees apart. It doesn't matter how big your groups are here and here, it's not going to change the geometry. The geometry is always going to be 180 degrees because that's as far apart as you can get anywhere. There's no thing changing it to bend it slightly. It'll always be 180 degrees. And again, this first bond here, don't forget, that first bond is a sigma bond. And the second one here is one of the P's, and this one here is the other of the P's, okay? So that 2 P's are in one axis bonding over and under to give us our pi bond, And then the other P is in the other axis, giving our double bond. So it's two sets of parallel bonds. Okay? So being that we only have dispersion forces, and being that we only have these nonpolar hydrogen carbon bonds and carbon-carbon bonds, they still have fairly low density. They are still tend to be less dense than water. They tend to not dissolve in water, but dissolve in each other. And they also tend to scale directly with the molecular weight of the compound. Okay. The only other thing these things do that is different from the alkanes is the idea that the alkyne hydrogen is really acidic in comparison. pKa at 25 is not very high. If you think about it, acetic acid has a pKa of 4.75, okay? We consider that an acid at room temperature. Water, it can be an acid or a base, and it's 14.5 or around 15, okay? So if we think of water as being an acid or a base, it's not that acidic. But for a hydrocarbon, the alkyne hydrogen is the most acidic. And we do have to use a very strong base. It's a nitrogen-based base with an anion on it. So it's one of our stronger Lewis bases to pull that hydrogen off to generate the acetylide ion. Notice we have to be very careful about which solvent we make the acetylide ion in. Because if we made the acetylide ion and then added something with water in it, it would immediately react with the water and we would regain our acetylene. So we have to have something that has a lower acidity than the acetylide, than the acetylene hydrogen here, or else it will react with the solvent. So we're going to see that there's a solvent selection process we'll go through when we start doing reactions where we're forming these anions, specifically carbon anions. We'll see that again and again. Okay? So we can't make this with hydroxide because the presence of water, it's too high. I'm sorry, I wrote right over the pKa there. It's a stronger acid than this is. So as soon as it hits water, it's going to go back to the acetylene. Okay, so we're going to, as we add new functional groups, we're going to look at the pKa and the relative values. Our sp3 hybridized hydrogen has the lowest acidity with the highest pKa value of 51. Alkenes are a little bit below that at 44, and the alkynes is our most acidic hydrocarbon at 25 pKa. All right, that is goal number 3, which is the physical properties and the types of bonding it does, okay? And, ooh, it's right at 1:40, unfortunately. So we're going to put the activity, the cyclohexane activity aside, and I will make sure we get those points by some other activity. I'll probably do it next week. Go ahead and review any of the videos and the goals before our exam tomorrow, and make sure you do your homework as a good practice for that. Are there any questions for this session? I know some people have to stay behind to talk about other things. But if you don't have any of those questions, you're free to leave, and I'm going to stop recording here.